Here is our next question, number 20. Find the transformer ratios A and B such that the impedance Zin is resistive and equals 2.5 ohms when the network is excited with a sine wave voltage of angular frequency of 5000 radians per second. Okay, so we have a figure given to us, and we see that we have two transformer ratios. On one end, we have 1:B. On the other end, we have 1:A. Now, we have to try to convert this entire figure into one equivalent circuit. So we'll do that step by step. Okay? So we will start from the very end on the right side here. Let's assume that the part on the left is the primary side and the part on the right is the secondary side. Okay? So if we consider this portion right here, just this portion. R is on the secondary side, and this side here is the primary side. Okay? So the first step is to write the resistance R, or shift the resistance from R from the secondary to the primary side. That's the first step. Shift R from secondary side to primary side. So what happens here is R becomes or turns to R by A square. The ratio here is A square. 1 by A, right? So it's R by A square. It's R by K square. That's the ratio, okay? Which is written here in terms of the ratio given, R by A square. Now, if we draw the circuit, this is what we are going to have now. The capacitance, that's the first part, primary. This is the secondary. Here we have the inductance. And now, we have brought this here, R by A square. I hope that makes sense. So here we have C, here we have L, and this is Zin. Now, we have resolved the entire figure and brought it down to a smaller figure. Now we have to convert the entire thing into a more equivalent circuit. So let's do that next. Next, let's shift the inductance here, L, from the secondary side to the primary side. Okay, we are going to do that next. Inductance L from secondary side to primary side. Now what do we have? L becomes L by B square. Why? If you notice, just as we did in the previous part here, take a look at this portion. If you take a look at this portion here, you will see that L, which is on the secondary side, if it has to be shifted to the primary, we use the same ratio here, which is L by K square. So K square in this case would be B square. So L by B square when it is shifted from the secondary to the primary. Okay? Now, I am going to draw the equivalent circuit of just one set of ratios. This is our capacitance. Now we have shifted L from the secondary to the primary, okay? Here is our primary winding. and we still have the resistance here, R by A square. This is L by B square. This is C, this is Z in. And the ratio here is 1:B. Okay, so now we have to figure out what the value of A is and what the value of B is. Let's start with B, since here we have the ratio of 1:B. Okay? Now, what is the rule for reactances in an equivalent circuit? You should know that XC must be equal to XL. This is an important relation. When we are calculating in terms of an equivalent circuit, the capacitive reactance must be equal to the inductive reactance. So, what's XC? 1 divided by omega C. And XL is, in this case, omega L by B square. XL is omega L. But here L is L by B square. So we substitute that here and we get it as omega L by B square. Now let's cross multiply and isolate B. We will obtain B square is equal to omega square LC, or B is equal to root omega square LC. I think we can leave it this way for now. Alright, so now the next step is to plug in the values of L, C and omega. The question gives us the values. I'll note it down here. Let's see. What are the values given to us? We have angular frequency omega is 5000 radians per second. And the capacitance is 10 microfarad. The inductance is 1 millihenry. Okay, got it. So here, C equals 10 microfarad. L equals 1 millihenry. R is given as 2.5 ohm. And omega is equal to 5000 radians per second. Z in is also given as 2.5 ohms according to the question. So these are the given values. We have found the expression for B as root of omega square LC. Let's substitute 5000 square into 1 into 10 power minus 3 into 10 into 10 power minus 6. Omega LC. Now if we solve this, what do we get? We should get root 0.25, and the square root of 0.25 is 0.5. So the value of B is 0.5. That's our first value. Now that we have the value of B, let's move on to find the value of A. Okay, so the question says that Z in is resistive. Now if we look at the equation the figure that we have drawn here, let's shift R by A square from the secondary to the primary to complete the equivalent circuit. Okay, let's do that now. Now we are going to shift R by A square from secondary side to the primary side. Look at the figure. Now you know the ratio quite well. The ratio is supposed to be R divided by K square. Now here we have R by A square. The ratio is 1:B. So what does that give us? That gives us r divided by a square b square. Okay? If you need more clarification, I can write it down here. So that's r by a square divided by k square. K square is b square here. That's what we have. Now I'll put that down here. So r by a square from the secondary side, when shifted to the primary side, it becomes r by a square divided by b square, which is r by a square b square. Now this is equal to Z in because it is resistive. Z in is equal to r by a square b square. So let's substitute the values of Z in, r and b, solve it to find the value of a. I hope this is clear so far. Alright. The expression is Z in is equal to r by a square b square. Let's substitute. 2.5 is equal to 2.5 divided by a square into 0.5 square. R is 2.5, Z in is also 2.5. Now, what would a square become? A square would be 1 by 0.5 square, right? 2.5 cancels out. Now solving this further, a is equal to 1 by 0.5, which equals to 2. So a equals 2. These are the final values. A equals 2 and b equals 0.5. This is the final answer. Now let's see which option it matches. It matches option B. So this is the entire solution.